And now we move on to insulation and roofing. So for mandatory measures, the following openings in the building envelope shall be caulked, gasketed, weather stripped, or otherwise sealed. The exterior joints between conditioned and unconditioned space, any openings for plumbing, electricity, and gas lines on exterior surfaces, any openings in the attic floor, and or any openings around exhaust ducts.
Weather stripping is required for all field fabricated operable windows and doors. This does include doors between the garage and living space, and doors for HVAC closets and attic accesses in the living space. All other such openings in the building envelope. So essentially, if there's a hole, there's an opening, there's a door, any way that that air can move from the outside to the inside of the home, it does need to be sealed, weather stripped, or caulked to prevent that movement of air. Now, continuous stucco, building wraps, and exterior rigid wall insulation can be used as an alternative technique to meet the mandatory caulking and sealing requirements.
So here we have the table that contains a prescriptive value. So here's the table from package A, and this is the walls section. You can see that it is broken down into a couple of different categories. We've got above grade and below grade walls, and then within those we have framed and mass, and then both for the mass walls and the below grade, whether it's an interior value or an exterior value. So let's look at the one that you'll most commonly see, and that's going to be an above grade framed wall. And we look at the different climate zones that we have, and we have two different sets of values. So if we look at climate zones 6 and 7, we're going to see a U factor of 0.065. So we're used to dealing with, most of the times we're looking at, R values for the insulation that's in the cavity or the exterior insulation. But for these walls in this package A, they're going to give an overall assembly U factor value as your target. So we're looking at not only the insulation that goes in the wall, we're going to look at the exterior coating, whether it's stucco or it's a lath sheathing. You're going to look at the drywall on the inside, the studs, any exterior insulation. So it's all those parts that make up that entire wall assembly is going to calculate a U factor. So our maximum target for above grade framed walls in climate zone 6 and 7 is 0.065, and in all other climate zones it's going to be 0.048. Now you might say, well, what kind of assemblies am I going to see? Well, how am I going to know if it's a 0.048? Luckily, as a HERS rater, you don't have to look at this. You don't have to verify it. It's going to be the local building inspector, but we will provide you with a couple of examples here next. And so here we have some of those examples. So if we saw climate zone 6 and 7, they had a max U factor of 0.065. So if we look at the first one on the list here, we've got 2x4 studs, R15 cavity insulation, which usually in a 2x4 wall we're used to seeing an R13. That R15 is going to have to be a high density bat to get that 15. We're going to have exterior insulation, so foam board on the outside of an R4, and that's going to allow us to achieve a 0.065 U factor. Now in all the other climate zones, we're looking for a 0.048. So that's a pretty low number to shoot for. You can see we got some more of these more standard type construction assemblies. The most common that we see is a 2x6 with an R19 bat and R5 on the outside, but that's only a 0.051, so that's not going to quite make it. If we go kind of the next step up, the same 2x6 wall with an R23, so a high density bat, and an R4, that gets us to an 049. So we're likely going to have to go with a 2x6 wall with R23 and R5 on the outside to hit that 0.048 target that we're looking for. Now again, these are prescriptive values, so a lot of builders, when they're doing new construction, they're going to use that performance method, and that's going to give them a little bit of flexibility. So maybe they're going to go with that 2x6 R23 with an R4 at an 049. It's going to be a little bit of a penalty, but they can make up for it elsewhere. So those are some examples of different wall construction assembly types and their associated U factors that you may see out there in the field.
Now the mandatory minimums, so we talked about prescriptive, the mandatory minimums for walls is an R13, a 2x4, and an R19, and a 2x6. Both of these minimums don't apply to frame walls of conditioned basement, crawl spaces that are below grade, and rim joists between stories are allowed to have R13 regardless of the wall size. So there are different values that are used to meet the criteria for metal frame assemblies and mass walls. We're not going to cover these. This presentation mainly covers just wood frame construction. However, if you want to look these up, the separate criteria that I just talked about can be found in the reference joint appendix JA4. Bad and loose fill insulation should fill the wall cavity evenly, and then insulation should extend into the perimeter floor joist cavities along the same plane as the wall, obviously to extend the insulation the furthest out in the wall. If a vapor retarder is required, it must be installed on the conditioned space side of the framing, so basically on the interior side of the wall. And then always the R value of the installed insulation should meet or exceed the values found on the CF1R. And I know that we're listing this in the wall insulation, but that's the case for any insulation. You should always match or exceed what's found on the CF1R. Now for the floor, it's easier, just an R19, prescriptively required throughout the state for floor installation. Obviously we're talking about a raised floor. The R19 is also the mandatory minimum for the state as well. So for floor installation, the mandatory minimum and the prescriptive requirement is the same, R19. Again, just like the walls, different type of raised floors, basement, crawl spaces, etc., have different installation requirements, and these separate requirements can be found again in reference joint appendix JA4. Now slab installation is a little different. So slab installation is prescriptively required in climate zone 16. So prescriptively, R7 slab installation is required in climate zone 16. And while not a mandatory measure, there is a product suitability requirement that can be found in Chapter 3 of the Residential Manual, Section 3.1.22. So depending how that installation is installed, there's different products that you have to use. As long as they are R7 in climate zone 16, though, you're fine. When slab installation is required by the prescriptive or performance approach, the minimum depth is 16 inch or to the top of the footing, whichever is less. And these are examples of where that installation would go. So on the top left hand side, you have interior insulation. On the top right hand side, you'll see how the insulation is placed on the outside of the raised floor. On the bottom left, the insulation is placed beneath the slab. And then in the bottom right, it's basically radiant floor insulation where the insulation is placed on top of the floor. Now, what we were talking about earlier, we were saying that each installation type has its own material product requirements. This is what we're talking about. So depending on where the installation is being installed, there's different products that are approved for that particular application. Now for heated slab installation, the radiant floor systems of the concrete slabs must have insulation between the heated portion of the slab and the outdoors. So don't confuse this with regular slab installation. In climate zone 16, the slab installation is prescriptively required whether that's a heated slab or not. But if you have a heated slab anywhere else in any other climate zone, the slab installation is also required because you have a heated slab. So basically here, this table shows you the climate zone on the right hand side and basically the installation R value based on the climate zone that you're in and how you're supposed to install it based on that scenario. And again, examples how the heated slab insulation would be installed, which is very similar to the other slide that we saw a second ago.
Now let's take a look at the prescriptive requirements for ceiling and roof insulation. So on the prescriptive side, we have two options which we can choose from. We have option B and option C. Now both of these are what we consider high performance options. They're not your standard ventilated attic with just insulation at the ceiling level itself. Both of these options employ more recent strategies to result in a better performing attic space and overall ceiling roof assembly. So for option B, we're going to have insulation installed in two different locations. So the first one is going to be at the underside of the roof deck, and then the second one is going to be at the ceiling level. Now each of these locations has a different R value requirement, and these are going to be dependent on the climate zone in which you're building, and we'll look at those here in a second. But you're going to have those in two different places. It's going to be a ventilated attic, and it's going to have insulation at both the underside of the roof deck as well as at the ceiling. The second option, which is option C, is ducts in conditioned space. So this allows you to build with a traditional attic, like what we're used to seeing, a ventilated attic. There's no insulation under the roof deck. All the insulation is just at the ceiling level itself. But you have to move all of your ductwork as well as your HVAC equipment into the conditioned space. So this can be done either by having a closet and various drop ceilings that the ducts run through, or you can include the HVAC equipment in a drop ceiling, and drop ceilings and soffits and chases, and all this ductwork is going to essentially be run on the inside of the building, but it can be covered with drywall and things of that nature, but it's going to be on the interior side of the insulation itself. So as I mentioned, each of these options is going to have R values associated with it that are dependent on the climate zones in which you're building, as well as the location of that insulation. So if we look at the first column there on the left, option B, single family, we're going to see that we need a vented attic. So it's going to be a regularly ventilated attic. We're going to need R19 in climate zones 4 and 8 through 16 below the roof deck. And this can be batts, spray and cellulose, fiberglass, that's secured with netting, spray foam. So it's not limited to one specific type of insulation. Any of those that can achieve that R19 value and is approved by the manufacturer for installation in that location can be used. And then we're going to see R38 required in climate zones 1, 2, 4, and 8 through 16. And then R30 in climate zones 3 and 5 through 7, and that's going to be for our ceiling insulation. So it's going to be at the ceiling itself. We are going to require radiant barrier in climate zones 2, 3, and 5 through 7, and those are going to be the climate zones where we saw the R19 below the roof deck. Those were climate zones 4 and 8 through 16. So all the other ones where that below roof deck insulation is not required, a radiant barrier needs to be installed. You can't have both a radiant barrier and below roof deck insulation. They just don't work together. So you're going to have either or. It also is going to require airspace between the roofing and the roof deck. This allows for more of that heat to get out of there, provides that air gap. And then either R6 or R8 duct insulation. Again, this is going to be based on your climate zone. And then for the duct leakage for those ducts, a 5% leakage is the maximum, and that's the standard for duct leakage in new duct systems. We see something very similar on the multifamily side. Again, a ventilated attic, and then R19 in climate zones 4, 8, and 9, and then 11 through 15. Or if you're in climate zones 10 or 16, you can be R13. R38, climate zones 1, 2, 4, 8 through 16, and then R30 and 3 and 5 through 7. Radiant barrier in those climate zones that don't require below roof deck insulation, which is 2, 3, and 5 through 7. Again, we're going to have that airspace, R6 or R8 duct insulation, and 5% leakage. Now moving over to option C, this is the ducts in conditioned space. You're still going to have that vented attic. You're going to be using R38 in climate zones 1 and 11 through 16, and R30 for climate zones 2 through 10. Again, this is at the ceiling only. There's no below roof deck insulation. R6 or R8 ducts, the same. Radiant barrier, we're going to see that in climate zones 2 through 15. So because we don't have below roof deck insulation in any of the climate zones, a majority of those are going to see that radiant barrier. It's only going to be 1 and 16, which are the most mild climates where we're not going to see that radiant barrier. And then you do have to take the HERS verified ducts in conditioned space credit. So that's a prescriptive requirement that belongs with this option C. If you take that credit, then you are going to have the HERS rater go out and verify those ducts in conditioned space. And here's what we would see looking at the prescriptive tables themselves, package A. Again, you can see over there on the left-hand side, we've got 3 different topics. We've got the below roof deck insulation with airspace, ceiling insulation, and radiant barrier. And you simply just find the climate zone which you're working in, and you'll see exactly what you need, whether it's everything or just one of the items or a mix and match. They're all listed there.
And finally, option C, again, climate zone specific. As we mentioned in that first table, we're going to have R30 required in climate zones 2 through 10, and then R38 in climate zones 1 and 11 through 16. Radiant barrier is going to be required in climate zones 2 through 15 for option C. So for our mandatory measures, the mandatory minimum is going to be R22 or an overall U factor of 0.043, and this will be for wood framed roofs only. There are different standards for metal roof and other roof assemblies, and those can be found in reference joint appendix JA4. And then we do have 3 different ways to meet the prescriptive requirements that we saw. The first one is just to meet the minimum prescriptive insulation standards. If it says R30, you install R30. Our option number 2 is to use a different roof assembly that can be found in JA4. There are metal roof assemblies, there are rafter type assemblies. So if you're doing something other than a standard wood framed roof, go to JA4 and meet the requirements that they have listed there. And then finally, you can use the Energy Commission's Easy Frame Assembly Calculator. That will give you the U factor of the type of assembly that you want to build, and as long as that assembly meets the minimum requirement or prescriptive requirements for U factors, then it will comply with the requirements.
Ceiling insulation should extend far enough to the outside walls to cover the bottom chord of the truss. So basically, it's made to extend the insulation out the furthest out possible. Loose fill insulation must be blown evenly. It also needs to meet the specified weight per square foot for the corresponding R value for fiberglass and mineral fiber only. And then insulation should not block the E-vents, and you have to use baffles to keep the vents unobstructed.
These E-vent baffles should be installed in 2 different locations. Now, if you don't have below deck insulation because you're using the ducts in conditioned space, you'd only need to put it in the first location. But if you do have both, then you'll need to have baffles in both of these locations. So you can see at the top of the wall where it intersects with the ceiling, there's that green line there. That is the vent baffle, and that's where the baffle is traditionally found. There's going to be a soffit vent in the soffit itself that's going to allow air to flow up and into the attic space, and then there'll be some vents higher up on the roof that allow that hot air to escape as it's replaced by this cooler air coming in from the soffit vent. So the purpose of these baffles is to direct the air around the insulation. Insulation will allow air to pass through it just like a filter would, and insulation cannot perform at its best if it has the air moving through it. It's just going to fill all the cavities with the same temperature air that's in the attic, and it's not going to separate it. So we want to direct it around, and we use these baffles to do that. So the first baffle there is going to take that air and it's going to direct it up along the bottom side of the roof deck and move it up towards the vent that's higher in the roof deck itself. When you have below deck insulation, you're going to need to install a second baffle or insulation stop that's going to then redirect that air from the underside of the roof deck kind of back down into the main body of the attic to allow it to then filter and mix with that air, and then it will eventually make its way to the top and out the upper vents. But we do need to have these baffles to keep that air from moving through that insulation and reducing the overall effective R value of that insulation.
And these are examples of baffles that you might see in the field. So on the left-hand side, it's simple cardboard baffle. In the middle example, those are actual baffles built specifically for that purpose. So it's product that is bought and installed for that specific purpose. And then on the right-hand side, looks like a field fabricated baffles, literally some cut 2x4s and plywood to keep the insulation in place and keep it from not covering the vents. So each one of these examples is perfectly okay, as long as it's doing what it's supposed to be doing.
The California Building Code requires a minimum vent area to be provided in roofs with attics, including enclosed rafter roofs creating cathedral or vaulted ceilings. Now, attic ventilation, particularly in hotter climate zones, can provide an energy benefit. The easier it is for the hot air to get out of the attic and be replaced by the cooler outside air, the lower the temperature is, the better job your insulation can do. However, there is no energy credit allowed for increasing the ventilation area above the building code requirements. You can model it, but there is no energy credit allowed through the performance method. Now, there are two options given within the CBC. Builders will need to check with the local jurisdiction because different jurisdictions will have different requirements. But that first option is to have your net-free ventilation area be not less than 1/300th of the area of the space ventilated. Now, the second option is going to be to have the net-free ventilating area be not less than 1/150th of the area of the space be ventilated. So either it's going to be 1 in 300 or 1 in 150. Again, it's going to be up to the local jurisdiction to decide which option they want. Now for option 2, that ratio can be reduced to 1 in 300 if a class 1 or 2 vapor barrier is installed on the warm-in winter side of the ceiling.
So in either situation, a minimum of 50% of the vents must be located in the upper portion of the space being ventilated and at least 3 feet above the eave or cornice vents. Ventilated openings are covered with corrosion-resistant wire cloth, screening, or similar mesh material. And then when part of the vent area is blocked by mesh or louvers, the resulting net-free area of the vent must be considered when meeting the ventilation requirements. So there's different standards for ventilating solid rafter spaces. So everything that we talked about as far as attic ventilation is concerned, we're talking about a regular attic. Now, a solid rafter space is an example of a cathedral ceiling or somewhere along those lines. So each framing cavity for a solid rafter space requires its own vent opening. There's different materials that will call for different approaches. And it's also at the discretion of the local building official. So there might be specific requirements depending on the climate zone, on the jurisdiction that the home is being built in. But keep in mind the solid rafter spaces are a separate application than the regular attic that we just talked about. There are additional insulation requirements that are present for QII, quality insulation installation, sprayed insulation, metal framing, log homes, straw bale construction, structural insulated panels or SIPs, or insulating concrete forms or ICFs. So we're going to be discussing a lot of these additional items in the QII section later on. So you'll hear some of these items again.
So as we saw, radiant barrier is prescriptively required in climate zones 2, 3, and 5 through 7 for option B, and 2 through 15 for option C. So what is radiant barrier? Radiant barrier is installed with the purpose of reducing the radiant gain to air distribution ducts and insulation below the radiant barrier. So it's going to be installed, as you can see in the picture there on the right. The radiant barrier is installed right at the underside of the roof deck. It does need to have space between the radiant barrier and anything below it. Anything in contact is just going to be a direct transfer of that heat. And radiant barrier works in such a way that the material itself does not release the heat. So if you go back to the basics of building science, we have the different types of heat transfer, and radiant or radiation is one of those three that we talked about. So this is a barrier. This is a material that doesn't release that heat, and so it stops it from going into that attic space. Any radiant barrier that's installed does have to meet the installation criteria that's specified in the residential appendices RA 4.2.1, and there's many different ways that it can be installed.
So the first application, like I said, pretty common in residential new construction. So basically the radiant barrier is actually part of the roof sheathing. It's installed just like a regular roof. The radiant barrier comes from the manufacturer on the underside of the roof sheathing and then just put on just like any other roof sheathing. Now in this particular installation type, it's a two-step approach. So they basically roll the radiant barrier over the trusses and then they put the roof sheathing over it. This application is more of a retrofit approach. It's actually used a lot in retrofit applications. I've also seen it used where the builder is supposed to put on a radiant barrier and they somehow forget, so they have to go back and put it on after the fact. But basically, it's the same type of material found in the second example that I showed you. The difference is the fact that the roof sheathing is already installed in this scenario. They just go back and basically fix pieces of radiant barrier below the actual roof deck around the trusses, and they staple it directly to the framing members. This last application, they rolled the radiant barrier, same type of material, they rolled the radiant barrier over the inside of the trusses under the roof deck. The one thing that I want to point out on this picture is the fact that the radiant barrier, when prescriptively required, needs to wrap the whole attic. It needs to wrap the whole attic, including gable ends. So in this particular picture, the gable end will also have to be wrapped in order to be compliant. Now, as far as cool roofs, they are prescriptively required. The prescriptive requirement depends on the climate zone and the slope of the roof. And there are two exceptions to the prescriptive requirements. So the roof area, one of those exceptions is the roof area has integrated PV panels, meaning that if there are integrated PV panels, you're not going to have roofing material over that particular area. Or the roof construction has a thermal mass over the roof membrane with a weight of at least 25 pounds per square foot. And these are the labels that you might see on roofing products. They have to be listed by the Cool Roof Rating Council directory, and obviously those values have to be applicable. And those are the two values that we're talking about, the solar reflectance and thermal emittance. Those are the values that you'll see on the CF1R telling you what the targets are supposed to be. This is the same principle as a window label, except that this is specific to roofing materials. Now this particular slide, it's really just here to show you the difference between a regular roof and a cool roof, and the fact that having a cool roof doesn't mean that you're limited to the colors of tile or product that you're going to be installing. So basically, by looking at the colors, you would think the darker colors would be worse off, and they are, but nonetheless, you could still have a cool roof that is black in color. So as you can see, the reflectance is still 0.41 versus a regular roof that's 0.04. Now, the black tile is obviously worse off scenario than a gray tile, but nonetheless, it can still be considered a cool roof depending on the manufacturer. So it's all about the manufacturer and the product that's being installed and not just the color of the tile.
The solar ready requirement is a mandatory measure. So this is going to apply to any new single-family residence that is in a subdivision with 10 or more residences, and to all new low-rise multifamily buildings.
What is the solar ready requirement? So the solar ready requirement require builders to build homes in such a way where a solar system could be dropped in without a lot of modifications to the house. The solar system doesn't have to be installed, but nonetheless, these requirements have to be met in order to make the house ready for a solar system if one ever wants to be added. So the solar ready requirement includes sub-requirements for the solar zone location, the solar zone area, the solar zone orientation, the shading, and the electrical. So for solar zone location, basically it has to do where the panels could go if they ever were put in. So they can be located on the roof of the building, on the overhang of the building. For single family and multifamily, that's what the SF and MF stands for. For multifamily, they could be located on the roof or overhang or other structures located within 250 feet of the primary building. They could be located on covered parking installed within the project, or also they could be on trellises, arbors, patio covers, carports, gazebos, and other similar accessory structures. So that's basically identifying where the panels would go. Once you identify where they would go, you have to designate a specific area that's going to be reserved for the solar panels. So it has to be clearly marked on the plans. This is for both single family and multifamily. It may be comprised of multiple areas, meaning that you can split it or you can have just one giant area, and that's specific to single family. The total cannot be less than 250 square feet, again, single family. And then for multifamily, the total area cannot be less than 15% of the total roof area of the building after subtracting any skylights from the roof area. And that's specific to multifamily. And then there are multiple exceptions that are present in the code for both single family and multifamily to kind of work around these requirements. So bottom line is, for single family, the solar area cannot be less than 250 square feet. For multifamily, it cannot be less than 15% over the total roof area of the building minus skylights. Once you identify where the area is and how big it's going to be, you have to make sure that that area meets a certain orientation. So if the steep slope roofs are used, they shall be orientated between 110 and 270 degrees of true north for both single family and multifamily. As long as they meet those particular orientation requirement, they're good to go. For low slope roofs, there are no orientation requirements. Now for shading, the solar zone shall be free from roof penetrations and any obstructions. Each obstruction needs to be a distance of at least 2 times its height from the solar zone. Any obstruction orientated north of all points of the solar zone is not subject to these requirements. And then any obstruction not located on the roof is not subject to these requirements as well. Now for electrical, the following needs to be present in the construction plans. There needs to be a plan for the location of the inverters and metering equipment. There has to be a pathway for routing conduit from the solar zone. There has to be a pathway for routing plumbing for water heating. So we don't actually have to install any of that. We just have to mark on the plans where those items will go. They just to be outlined to show where they would go if they were ever dropped in, but they're not actually being installed. You're not installing conduit. They're not installing plumbing. They're not installing any equipment. They're just marking where those items will go. Now for single family residences, they need to have a main electrical service panel with a minimum busbar rating of 200 amps and shall have a reserve marked for future solar electric space to allow installation of a double pole circuit breaker. So that electrical panel actually does need to be installed in single family residences. And that's because obviously if they have to ever drop in the solar panel, they have to have a way to wire it into. So that has to be there, and that's specific to single family. So let us know if you have any questions via the messaging system, or shoot us an email or give us a call. There was definitely a lot of information covered in this PowerPoint, and this is new material to you. I would be surprised if there was no questions. So feel free to reach out to us or save your questions for the field training, so you'll be able to ask the questions to your field trainer.